Okay, welcome back to lecture 8. So as they say, time flies. We've learned a whole lot of stuff already, right? In the past 8 lectures, we've learned vectors on how to add them, subtract them, scale them, resolve them into components and drawing them and all these different things about magnitude and directions of vectors, the whole theory, everything there. And then we learned about forces, all the different types, and how do you even tabulate all the force on one object that it experiences. So basically by asking the 2 questions of what are the contact forces and what are the non-contact forces on it. Everything that touches it will potentially produce a contact force. Anything that doesn't touches it, well, there's only one. There is the weight. So far we have learned that on it, and then we've learned that how to, after we know all the forces on an object, how do we add them together to find the net force, and then we suddenly shift gears into kinematics and learned all the different variables over here. So there's a whole lot of stuff, right? So this is the point where it could get confusing, right? A lot of people say physics is confusing. And in my experience, almost half the time when people say that, well, there are a couple of reasons why people would think that physics is confusing. Either you don't know what the word means, or you don't know what a concept means, or you don't know where how the concepts are put together and what is the point or where are you going with this. And in my experience, almost half of the time, it's the latter. And this is what traditional physics courses or traditional physics textbooks don't do too well, it looks like all disjointed concepts. When you learn other subjects like biology or economics or geography or something else, right? Sometimes there's a good story, or you kind of know where things are going. You know why these things are useful. In biology, you're learning about the human body and things like that. But in physics, it seems like all over the place, all the different concepts. So not saying that other 2 reasons of getting confused is not valid, right? A lot of times those are also valid, but particularly number 3 about putting things together in knowing where you're going. That is one of the things where a lot of traditional courses don't do too well. So it's always important to every now and then, immediately, or even better, every lecture, ask yourself, where are we and where are we going, right? It's also a general good life advice if you want to be successful in life. Just wake up every day in the morning and ask yourself, where am I and where am I going in my life? But this is not a philosophy class, this is a physics class. So let's ask these questions in the context of this course, right? So we have a very well-defined idea of what we want to do. We want to predict the future. And being a scientist, this is also one thing we want you to learn, right? Not necessarily you're being potentially forced and coerced into taking a physics class. Why do you care? You don't necessarily may never need to see these formulas again in your life. But what you want to learn is the way of thinking, how to take problems and break it down, or even how do you formulate problems, right? So let's say I have a goal. I want you to predict the future, and you immediately should ask me back, well, I don't know how to do that until you tell me what you want me to measure. If you don't have a precise wording and just say predict the future, that's astrology, not physics or science, right? To be proper science, you need to tell me what are the things that are measurable so that I can go out and actually measure it and test my theory, right? So everything is testable. That means you want to make your language precise, right? So let's see what are the languages and what are the topics we learned so far. Well, we learned the mathematics of vectors. So that's really just setting the scene, not really fit into this whole story of predicting the future, but it's a tool that we will use, right? We start with forces. So if we want to know what happens in the future, what is the main ingredient that affects the future? And Newton taught us, and it is a theory that worked for the past 300 years extremely well, is forces. And so we understand the definition of it, right? And we understand the special properties, especially with the first and second law is the most important, about motion of one object. We will get to his last and third law, but that is to do with motion between 2 objects. We want to focus on a very specific task first, on one object's motion. We realize that force is not required to generate motion. If something is already moving, it will move. Force is required to change the motion. And what does it change? And not only force, but it's net force, right? It's a net force on something. So if I apply 10 newtons of force on something and another 10 newtons, what will it do to the object? The answer is you don't know. You need to know the direction, right? If they counteract each other, there's no net force. But if there is a net force, then it will create what? It doesn't create velocity, because velocity does not require force. It creates acceleration, which is the change in velocity, right? So it will change the velocity of an object, and by this amount. And mass is basically the number that tells you how much it is. Newton's second law is actually better interpreted this way. It's just not as convenient and not as, it doesn't roll off the tongue as easy to say, A equals to F net over M, but this is how you should look at it, is we find out the force on it, and then we use that to find acceleration, right? So usually what we want to find is on the left, and so usually on the right-hand side of an equation, we put the things that we know, and on the left-hand side, we get the result that we want. Out of this, if you always say F equals ma, I don't like it. It's easy to remember, but it kind of implies the other way around. Usually, you're not trying to find the force. Usually, you want to know what's the acceleration. All right. So usually, we've talked about how to find the force. Is basically anything that's on contact, and also there's a special one, a non-contact force. Once you know the force, you can find the acceleration. And once you know the acceleration, usually if you want to predict the future, what else is about the initial state is the initial velocity, right? So once you have 2 out of these 5 things, you still can't predict the future, but you need 3 out of 5. Once you have the 3, you'll find out everything you need. Okay, so depends. Sometimes you want to throw a ball a certain distance, or you know what displacement you want, and then you can find out how long it takes, or what's the final velocity when you get there, or you know the final velocity you want something to hit, right? If you, let's say, shoot an arrow, or if you shoot a gun, you want to know, I want a certain final velocity. I want to know how long it takes to get there, or what distance it will be able to go, or something like that. So usually not. So usually you'll be given these in practice. Usually you will have these 2 and 1 more, and then find out everything else later. Of course, in a homework or a test, you might actually be given something else and then find these 2. But that's really just to test your familiarity with the equations and how to manipulate them, but not necessarily in practice. Usually there's it's going in this direction. Okay. All right. So far we learned everything we need to know about 1D, and that is pretty simple, right? We just use the 4 kinematics equation, and you can find out the result. And now today, basically, our job is to move on to 2D. And you will, on the first glance, you will think that 2D will be really complicated, because now suddenly it can go in all different directions. But there's one simple principle we'll mention later that makes 2-dimensional problems. If you can handle 1-dimensional ones, 2-dimensional ones, it's just almost exactly the same, right? So we'll see how that works, okay? And then where we're going with this is, this sort of completes our journey. After today, we'll complete our journey about how to measure something initially and find out something in the future for one object. And then we'll move on to look at things with situations where there's 2 objects. And if you can do 2, you can do more than 2. All right. So that's sort of the goal of where we're at. And we'll jump right into 2D motions.